Generic types, traits, and lifetimes. Every programming language has tools for effectively handling the duplication of concepts. In Rust, one such tool is generics. Generics are abstract stand-ins for concrete types or other properties. When we're writing code, we can express the behavior of generics, or how they relate to other generics without knowing what will be in their place when compiling and running the code. Similar to the way a function takes parameters with unknown values to run the same code on multiple concrete values, functions can take parameters of some generic type instead of concrete type, like I32 or string. In fact, we've already used generics in Chapter 6 with option T, Chapter 8 with vector T and hash map KV, and Chapter 9 with result TE. In this chapter, you'll explore how to define your own types, functions, and methods with generics. First, we'll review how to extract a function to reduce code duplication. Next, we'll use the same technique to make generic functions from two functions that differ only in the types of their parameters. We'll also explain how to use generic types in Struct and Enumeration Definitions. Then you'll learn how to use traits to define behavior in a generic way. You can combine traits with generic types to constrain a generic type to only those types that have a particular behavior as opposed to just any type. Finally, we'll discuss lifetimes, a variety of generics that give the compiler information about how references relate to each other. Lifetimes allow us to borrow values in many situations while still enabling the compiler to check that the references are valid. Removing duplication by extracting a function. Before diving into generic syntax, let's first look at how to remove duplication that doesn't involve generic types as types by extracting a function. Then we'll apply this technique to extract a generic function. In the same way that you recognize duplicate code to extract into a function, you'll start to recognize duplicate code that can use generics. Consider a short program that finds the largest number in a list as shown in listing 10-1. Listing 10-1, code to find the largest number in a list of numbers. This code stores a list of integers in the variable number_list and places the first number in the list in a variable named largest. Then it iterates through all the numbers in the list, and if the current number is greater than the number stored in largest, it replaces the number in the variable. However, if the current number is less than or equal to the largest number seen so far, the variable doesn't change, and the code moves on to the next number in the list. After considering all the numbers in the list, largest should hold the largest number, which in this case is 100. To find the largest number in two different lists of numbers, we can duplicate the code in listing 10-1 and use the same logic at two different places in the program as shown in listing 10-2. Listing 10-2, code to find the largest number in two lists of numbers. Although this code works, duplicating code is tedious and error-prone. We also have to update the code in multiple places when we want to change it. To eliminate this duplication, we can create an abstraction by defining a function that operates on any list of integers given to it in a perimeter. This solution makes our code cleaner and lets us express the concept of finding the largest number in a list abstractly. In listing 10-3, we extract the code that finds the largest number into a function named largest. Unlike the code in listing 10-1, which can find the largest number in only one particular list, this program can find the largest number in two different lists. Listing 10-3 abstracted code to find the largest number in two lists. The largest function has a parameter called list, which represents any concrete slice of I32 values that we might pass into the function. As a result, when we call the function, the code runs on the specific values that we pass in. In sum, here are the steps we took to change the code from listing 10-2 to listing 10-3. Identifying duplicate code, extract and duplicate code into the body of the function and specify the inputs and return values of the code in the function signature. Update the two instances of duplicate code to call the function instead. Next, we'll use the same steps with generic to reduce code duplication in different ways. In the same way that the function body can operate on abstract list instead of specific values, generics allow code to operate on abstract types. For example, say we had two functions, one that finds the largest item in a slice of I32 values and one that finds the largest item in a slice of character values. How would we eliminate the duplication? Let's find out. Generic data types. We can use generics to create definitions for items like functions, signatures, or structs. We can then use with many different concrete data types. Let's first look at how to define functions, structs, enumerations, and methods using generics. Then we'll discuss how generics affect code performance. In function definitions, when defining a function that uses generics, we place the generics in the signature of the function, where we would usually specify the data types of the parameters and return value. Doing so makes our code more flexible and provides more functionality to callers of our function while preventing code duplication. Continuing with our largest function, listing 10-4, shows how two functions that both find the largest value in a slice. Listing 10-4, two functions that differ only in their names and the types in their signatures. The largest _I32 function is the one we extracted in listing 10-3 that finds the largest I32 in the slice. The largest _character function finds the largest character in a slice. The function bodies have the same code, so let's eliminate the duplication by introducing a generic type parameter in a single function. To parameterize the types in the new function we'll need to name the type of parameter. Just as we do for the value parameters to a function, you can use any identifier as a type parameter name. But we'll use T because by convention parameter names in Rust are short. often just a letter, and Rust's type naming convention is camel case. Short for type, T is the default choice of most Rust programmers. When we use a perimeter in the body of a function, we have to declare the perimeter name in the signature so the compiler knows what the name means. Similarly, when we use a type perimeter name in a function signature, we have to declare the type of perimeter name before we use it. To define a generic largest function, place type name declarations inside angle brackets between the name of the function and the perimeter list like this. We read this definition as the function largest is generic over some type T. This function has one perimeter named list, which is a slice of values of type T. The largest function will return a value of the same type T. Listing 10-5 shows the combined largest function definition using the generic data type in its signature. The listing also shows how we can call the function with either a slice I32 values or character values. Note that this code won't compile yet, but we'll fix that in this chapter. Listing 10-5, a definition of the largest function that uses generic type perimeters but doesn't compile yet. If we compile this code right now, we'll get an error. The note mentions standard library CMP partial ORD, which is a trait. We'll talk about traits in the next section, but for now this error states that the body of largest won't work for all possible types that T could be. Because we want to compare values of type T in the body, we can only use types whose values can be ordered. To enable comparisons, the standard library has the standard CMP partial ORD trait that you can implement on types. See Appendix C for more on this trait. You'll learn how to specify that a generic type has a perimeter trait in the Traits are as Perimeters section. But let's first explore other ways of using generic type perimeters. In Struct Definitions, we can also define structs to use a generic type perimeter in one or more fields using the less than and greater than syntax. Listing 10-6 shows how to define a point T struct to hold x and y coordinate values of any type. Listing 10-6, a point T struct that holds x and y values of type T. The syntax for using generics in struct definitions is similar to that used in function definitions. First, we declare the name of the type perimeter inside the angle brackets just after the name of the struct. Then we can use the generic type in the struct definition where we would otherwise specify concrete data types. Note that because we used only one generic type to define point T, this definition says that the point T struct is generic over some type T and that the fields x and y are both that same type. Whatever the type may be, if we create an instance of a point T that has a value of different types as in listing 10-7, our code won't compile. Listing 10-7, the fields x and y must be the same type because both have the same generic data type T. In this example, when we assign an integer value 5 to x, we let the compiler know that the generic type t will be the integer for the instance of point t. Then we specify 4.0 for y, which we can define to have the same type as x. We'll get a mismatch error like this. To define a point struct where x and y are both generics but could have different types, we can use multiple generic type parameters. For example, in listing 10-8, we can change the definition of point to be a generic over types t and u, where x is of type t and y is of type u. Listing 10-8, a point t u generic over types so that x and y can be values of different types. Now all the instances of point shown are allowed. You can use as many generic type parameters in a definition as you want, but using more than a few makes your code hard to read. When you need lots of generic types in your code, you could indicate that your code needs restructuring into smaller pieces. In enumeration definitions, as we did with structs, we can define enumerations to hold generic data types in their variants. Let's take another look at the option T enumeration that the standard library provides, which we used in Chapter 6. This definition should make more sense to you. As you can see, option T is the enumeration that is generic over type T and has two variants: some, which holds one value of type T, and none variant that holds any value. But using the option T enumeration, we can express the abstract concept without having an optional value. And because option T is generic, we can use the abstraction no matter what type of the optional value is. Enumerations can multiply generic types as well. The definition of the result enumeration that we used in Chapter 9 is one example. The result enumeration is generic over two types, T and E, and has two variants: OK, which holds a value of type T, and error, which holds a value of E. This definition makes it convenient to use the result enumeration anywhere we have an operation that might succeed, return a value of some type T, or fail, return of error of some type E. In fact, this is what we used to open a file in listing 9.3, where T was filled in with the type standard library fs file when the file was opened successfully, and E was filled in with the type standard library input output error. When there were problems opening the file. When you recognize situations in your code with multiple structs or enumerations, definitions that differ only in types of values they hold, you can avoid duplication by using generic types instead. In method definitions, we can implement methods on structs and enumerations as we did in Chapter 5 and use generic types in their definitions too. Listing 10-9 shows the point T struct we defined in listing 10-6 with a method named X implementation on it. Listing 10-9 implementing a method named X on the point T struct that return a reference to the X field of type T. Here we've defined a method named X on point T that returns a reference to data in the field X. Note that we have to declare T just as after impl so that we can use it to specify that we're implementing methods on the type pointer point T. By declaring T as a generic type after impl, Rust can identify that type of angle brackets in point is a generic type rather than a concrete type. We could, for example, implement methods only on point F32 instances rather than on point T instances with a generic type. In listing 10-10, we use a concrete type F32, meaning we don't declare any types after impl. Listing 10-10 an impl block that only applies to a struct with a particular concrete type for a generic type parameter T. This code means the type point F32 will have a method named distance underscore from underscore origin, and that other instances of point T where T is not of type F32 will not have this method defined. The method measured how far our point is from the point at coordinates 0, 0, 0.0 and uses mathematical operations that are available only for floating point types. Generic type parameters in a struct definition aren't always the same as those you use that struct's method signatures. For example, listing 10-11 defines the method mixup on the point T you struct from listing 10-8. The method takes another point as a parameter which might have different types from the self point we are calling mixup on. The method creates a new point instance with the x value from the self point of type T and the y value from the passed in point of type W. Listing 10-11, a method uses different generic types from its struct's definition. In main, we defined a point that has an I32 for x with a value of 5 and an F64 for y with a value of 10.4. The P2 variable is a point struct that has a stringing slice for x with the value hello and a character for y with a value C. Calling mixup on P1 with an argument P2 gives us P3, which will have an I32 for x because x came from P1. The P3 variable will have a character for y because y came from P2. And let's see, the print line macro call will print p3.x equal 5, p3.y equals c. The purpose of this example is to demonstrate a situation in which some generic parameters are declared with impl and some are declared with the method definition. Here the generic parameters t and u are declared after impl because they go with the struct's definition. The generic parameters v and w are declared after fn function mixup because they're only relevant to the method. Performance of code using generics. You might be wondering whether there's a runtime cost when you're using generic type parameters. The good news is Rust implements generics in such a way that your code doesn't run any slower using generic types than it would with concrete types. Rust accomplishes this by performing metaphorization of the code that is using generics at compile time. Metaphorization is the process of turning generic code into specific code by filling in the concrete types that are used when compiled. In this process, the compiler does the opposite of the steps we used to create the generic function in the listing 10-5, the compiler looks at all the places where generic code is called and generates code for the concrete types the generic code is called with. Let's look at how this works with an example that uses the standard library's option T enumeration. When Rust compiles this code, it performs morphization. During the process, the compiler reads the values that have been used for option T instances and identifies two kinds of option T. One is I32 and the other is F64. As such, it expands the generic definitions of option T into the option underscore I32 and the option underscore F64, thereby replacing the generic definition with the specific ones. The monomorphized version of the code looks like the following. The generic option T is replaced with the specific definitions created by the compiler. Because Rust compiles generic code into code that specifies the type in each instance, we pay no runtime cost for using generics. When the code runs, it performs just like it would if we had duplicated each definition by hand. The process of monomorphization makes Rust generics extremely efficient at runtime. Traits defining shared behavior. A trait tells Rust compiler about functionality a particular type has and can share with other types. We can use traits to define shared behavior in an abstract way. We can use trait bounds to specify that a generic can be any type that has certain behavior. Note, traits are similar to a feature often called interfaces in other languages, although with some differences. Defining a trait. A trait's behavior consists of methods we can call on that type. Different types share the same behavior. If we can call the same methods on all those types, trait definitions are a way to group method signatures together to define a set of behaviors necessary to accomplish some purpose. For example, let's say we have multiple structs that hold various kinds of amounts of text. A news article struct that holds a news story field in a particular location with a tweet that can have at most 280 characters, along with metadata that indicates whether it was a new tweet or retweeted or a reply to another tweet. We want to make a media aggregator library that can display similarities of data that might be stored in a news article or tweet instance. To do this, we need a summary of each type, and we need to request that summary by calling a summarize method on an instance. Listing 10-12 shows the definition of summary trait that expresses this behavior. Listing 10-12, a summary trait that consists of the behavior provided by a summarized method. Here we declare a trait using the trait keyword and then the trait's name, which is summary in this case. Inside the curly brackets we declare the method signatures that describe the behaviors of the types that implement this trait, which in this case is fn function, summarize ends referring to self, and arrow string. After the method signature, instead of providing an implementation with curly brackets, we use a semicolon. Each type implementing this trait must provide its own custom behavior for the body of the method. The compiler will enforce any type that has the summary trait will have the method summarize defined with this signature exactly. A trait can have multiple methods in its body. The method signatures are listed one per line, and each line ends in a semicolon. Implementing a trait on a type. Now that we've defined the desired behavior using the summary trait, we can implement it on the types in our media aggregator. Listing 10-13 shows an implementation of the summary trait on news article struct that uses the headline, the author, and the location to create the returned value of summarize. For the tweet struct, we use summarize as the username followed by the entire text of the tweet, assuming that the tweet content is already limited to 280 characters. Listing 10-13, implementing the summary trait on the news article and tweet types. Implementing a trait on a type is similar to implementing regular methods. The difference is that after implementation, we can put the trait name that we want to implement, then use the for keyword, and then specify the name of the type we want to implement for the trait for. Within the impl block, we put the method signatures that the trait definition has defined. Instead of adding a semicolon after each signature, we use curly brackets and fill in the method body with the specific behavior we want and methods of the trait to have for the particular type. After implementing the trait, we can call the methods on instances of news article and tweet in the same way we call regular methods like this. This code prints one new tweet, horse_ebooks. Of course, as you probably already know, people. Note that because we define the summary trait and the news article and tweet types in the same lib.rs in listing 10-13, they're all the same scope. Let's say that this lib.rs is for a crate we've called aggregator, and someone else wants to use our crate functionality to implement the summary trait on a struct defined within their library scope. They would need to bring the trait into their scope first. They would do so by specifying user aggregator : summary : which then would enable them to implement summary for their type. The summary trait would also need to be a public trait for another crate to implement, which it is because we put the pub keyword before trait in listing 10-12. One restriction to note with trait implementations is that we can implement a trait on a type only if either the trait or the type is local to our crate. For example, we can implement standard library traits like display on a custom type like tweet as part of our aggregator crate functionality. Because the type tweet is local to our aggregator crate, we can also implement summary on vector t, vec_t, in our aggregator crate because the trait summary is local to our aggregator crate. But we can implement external traits on external types. For example, we can't implement external traits on external types. For example, we can't implement display trait on vector t within our aggregator crate because display and vector t are defined in the standard library and aren't local to our aggregator crate. This restriction is part of the property of programs called coherence, and more specifically the Orphan Rule, so named because the parent type is not present. This rule ensures that other people's code can't break your code and vice versa. Without the rule, two crates could implement the same trait for the same type and Russ wouldn't know which implementation to use. Default implementations. Sometimes it's useful to have default behavior for some or all of the methods in a trait instead of requiring implementations for all methods on every type. Then as we implement the trait on a particular type, we can keep or override each method's default behavior. Listing 10-14 shows how specifically a default string for a summarize method of the summary trait instead of only defining the method signature as we did in listing 10-12. Listing 10-14 definition of a summary trait with a default implementation of the summarize method. To use a default implementation to summarize instance of news article instead of defining a custom implementation, we specify an empty impl block with impl summary for news article. Even though we're no longer defining the summarize method on news article directly, we've provided a default implementation of specified in that news article implements the summary trait. As a result, we can still call the summarize method on an instance of news article like this. This code prints new article available. Read more. Creating a default implementation for summarize doesn't require us to change anything about the implementation of summary on tweet. In listing 10-13, the reason that the syntax for overriding a default implementation is the same as the syntax for implementing a trait method doesn't have the default implementation. Default implementations can call other methods in the same trait, even those other methods don't have the default implementation. In this way, a trait can provide a lot of useful functionality and only require implementers to specify a small part of it. For example, we could define the summary trait to have a summarized _author method whose implementation is required, and then define a summarize method that has the default implementation that calls the summarize _author method. To use this version of summary, we only need to define summarize _author when we implement the trait on a type. After we define summarize _author, we can call summarize on the instance of the tweet struct, and the default implementation of summarize will call the definition of summarize _author that we've provided. Because we've implemented summarize _author, the summary trait has given us the behavior of the summarize method without requiring us to write any more code. This code prints one new tweet. Read more from @horse_ebooks. Note that it isn't possible to call the default implementation from an overriding implementation that same method. Traits as parameters. Now that you know to define the implement trait, we can explore how to use traits to define functions that accept many different types. For example, in listing 10-13, we implemented the summary trait on the news article and tweet types. We can define a notify function that calls a summary method on its item parameter, which is some type that implements the summary trait. To do this, we can use the impl trait syntax like this. Instead of a concrete type for the item parameter, we specify the impl keyword in the trait name. This parameter accepts any type that implements the specific trait. In the body of notify, we can call any method on item that comes from the summary trait, such as summarize. We can call notify and pass in any instance of news article or tweet. Code that calls this function with any other type, such as a string or an I32, won't compile because those types don't implement summary. trait-bound syntax. The impl trait syntax works for straightforward cases, but is actually syntax sugar for a longer form, which is called a trait-bound. It looks like this. This longer form is equivalent to the example in the previous section, but is more verbose. We place trait bounds with the declaration of the generic type perimeter after a colon and inside angle brackets. The impl trait syntax is convenient and makes it more concise code. In simple cases. The trait-bound syntax can express more complexity in other cases. For example, we can have two perimeters that implement summary. Using the impl trait syntax looks like this. If we want this function to allow item 1 and item 2 to have different types, using impl trait, trait would be more appropriate, as long as both types implement summary. If we want to force both perimeters to have the same type, that's only possible to express using a trait bound like this. The generic type T, specified as the type of item 1 and item 2 perimeters, constrains the function such that the concrete type of the value passed as an argument for item 1 and item 2 must be the same. Specifying multiple trait bounds with the plus syntax, we can also specify more than one trait bound. Say we wanted to notify to use display formatting on item, as well as summarize method. We specify in the notify definition that the item must implement both display and summary. We can do so by using the plus syntax. The plus syntax is also valid with trait bounds on generic types. With the two traits bound specified, the body of notify can call summarize and use the curly brackets to format item. Clearer trait bounds with where clauses. Using too many trait bounds has its downsides. For generic has its own trait bounds. So function with multiple generic types, generic type perimeters can contain a lot of trait bound information between the function's name and its perimeter list, making the function signature hard to read. For this reason, Rust has alternate syntax for specifying trait bounds inside where cause after the function signature. So instead of writing this, we can also use a where clause like this. This function's signature is less cluttered. The function name, perimeter list, and return type are close together, similar to a function without lots of trait bounds. Returning types that implement traits. We can also use the implement trait syntax to return position syntax in the return position to return a value of some type that implements a trait as shown here. By using impl summary for the return type, we specify that the return underscore summarizable function returns some type that implements the summary trait without naming the concrete type. In this case, returns underscore summarizable returns a tweet, but the code calling this function doesn't know that. The ability to return a type that is only specified by the trait that implements it is especially useful in the context of closures and iterators, which we'll cover in Chapter 13. Closures and iterators create types that only that only the compiler know, or types that are very long to specify. The infiltrate syntax lets you concisely specify that a function returns some type that implements the iterator trait without needing to write out a very long type. However, you can only use infiltrate if you're returning a single type. For example, this code returns either a news article or a tweet, with a return type specified as impulse summary wouldn't work. Returning either a news article or a tweet isn't allowed due to the restrictions around how the infiltrate syntax is implemented in the compiler. We'll cover how to write a function with this behavior in the using traits objects that allow for values of different types in section of chapter 17. Fixing the largest function with trait bounds. Now that you know how to specify the behavior you want to use using the generic type parameters bounds, let's return to listing 10-5 to fix the definition of the largest function that uses a generic type parameter. Last time we tried to run that code, we received an error. In the body of the largest, we wanted to compare two values of type t using the greater than operator because the operator is defined as default method on standard library trait. Standard library CMP partial ORD. We need to specify partial ORD in the trait bounds for t so the largest function can work on slices of any type that we can compare. We don't need to bring partial ORD into scope because it's in the prelude, changing the signature of the largest to look like this. This time we compiled the code, we get a different set of errors. The key line in this error is cannot move out of type T, a non-copy slice. With our non-generic versions of the largest function, we were only trying to find the largest I32 or character, as discussed in the stack-only data copy section of chapter 4. Types like I32 and character that have a known size can be stored on the stack, so they implement the copy trait. But when we made the largest function generic, it became possible for the list parameter to have types in it that don't implement the copy trait. Consequently, we wouldn't be able to move the value out of list 0 and into the largest variable, resulting in this error. To call this code with only those types that implement the copy trait, we can add copy to the trait bounds of t listing. 10-15 shows the complete code of a generic largest function that will compile as long as the types of the values in the slice that we passed into the function implementation, the partial ORD and copy traits like I32 and characters do. Listing 10-15, a working definition of the largest function that works on any generic type that implements the partial ORD and copy traits. If we don't want to restrict the largest function to the types that implement the copy trait, we could specify that t has the trait bound clone instead of copy. Then we could clone each value in the slice when we want the largest function to have ownership. Using the clone function means we're potentially making more heap allocations in the case of types that own heap data like string. The heap allocations can slow if we're working with large amounts of data. Another way we could implement largest is for the function to return a reference to a t value in the slice. If we change the return type to and t instead of t, thereby changing the body of the function to return a reference, we wouldn't need the clone or copy trait bounds, that we could avoid heap allocations and implementing these alternate solutions on your own. Using trait bounds to conditionally implement methods. By using a trait bound with an impl block that uses generic type parameters, we can implement methods conditionally for types that implement the specific traits. For example, the type pair t in listing 10-16 always implements the new function, but pair t only implements the cmp underscore display method if its inner type t implements the partial ord trait that enables comparison and display trait that enables printing. Listing 10-16 conditionally implement methods on a generic type depending on trait bounds. We can also conditionally implement a trait for any type that implements another trait. Implementations of a trait on any type that sacrifices the trait bounds are called blanket implementations and are exclusively used in Rust standard library. For example, the standard library implements the toString trait on any type that implements the display trait. The impl block in the standard library looks similar to this code. Because the standard library has this blanket implementation, we can call the to_string method defined by the toString trait on any type of implementation to display trait. For example, we can turn integers into their corresponding string values like this because integers implement display. Blanket implementations appear in the documentation for the trait in the implementers section. Traits and trait bounds let us write code that uses generic type parameters to reduce duplication, but also specify to the compiler that we want the generic type to have a particular behavior. The compiler can then use the trait bound information to check that all the concrete types used with our code provide the correct behavior. In dynamically typed languages, we could get an error at runtime if we provide the In dynamically typed languages, we could get an error at runtime if we called a method on a type which didn't implement the type which defines the method. But Rust moves these errors to compile time, so we're forced to fix the problem before our code is even able to run. Additionally, we don't have to write code that checks for behavior at runtime because we've already checked at compile time. Doing so improves the performance without having to give up the flexibility of generics. Another kind of generic that we've already been using is called lifetimes. Rather than ensuring that a type has a behavior we want, lifetimes ensure that references are valid as long as we need them to be. Let's look at how lifetimes do that. Validating references with lifetimes. One detail we didn't discuss in the references and borrowing section of Chapter 4 is that every reference in Rust has a lifetime, which is the scope for which the reference is valid. Most of the time, lifetimes are implicit and inferred, just like most of the time types are inferred. We must annotate types when multiple types are possible. In a similar way, we must annotate lifetimes when the lifetimes of references could be related in a few different ways. Rust requires us to annotate the relationships in generic lifetime parameters to ensure the actual reference used at runtime will definitely be valid. The concept of lifetimes is somewhat different from tools in other programming languages, arguably making lifetimes Rust's most distinctive feature. Although we won't cover lifetimes in their entirety in this chapter, we'll discuss common ways you might encounter lifetime syntax so you can become familiar with concepts. Preventing dangling references with lifetimes. The main aim of lifetimes is to prevent dangling references, which cause a program to reference data in other than the data's it's intended to reference. Consider the program in listing 10-17, which has an outer scope and an inner scope. Listing 10-17, an attempt to use a reference whose value has gone out of scope. Note the examples in listing 10-17, 10-18, and 10-24 declare variables without giving them an initial value. So the variable name exists in the outer scope. At first glance, this might appear to be in conflict with Rust having no null values. However, if we try to use a variable before giving it a value, we'll get a compile time error which shows that Rust indeed does not allow null values. The outer scope declares a variable named R with no initial value, and the inner scope declares a variable named X with the initial value of 5. Inside the inner scope, we accept to set the value of R as a reference to X. The inner scope ends, and we attempt to print the value in R. This code won't compile because the value of R is referring has gone out of scope before we tried to use it. Here is the error message. The variable X doesn't live long enough. The reason is that X will be out of scope when the inner scope ends on line 7, but the R is still valid for the outer scope because its scope is larger. We say that it lives longer. If Rust allowed this code to work, R would be referencing memory that was deallocated when X went out of scope. And anything we tried to do with R wouldn't work correctly. So how does Rust determine what code is valid? It uses a borrow checker. The borrow checker. The Rust compiler has a borrow checker that compares scopes to define whether all borrows are valid. Listing 10-18 shows the same code as listing 10-17, but with annotations showing the lifetimes of the variables. Listing 10-18 annotates annotations of the lifetimes of R and X named A and B respectively. Here we've annotated the lifetimes of R and A and the lifetime of X with B. As you can see, the inner B block is much smaller than the outer A lifetime block. At compile time, Rust compares the size of the two lifetimes and sees that R has a lifetime of A, but that refers to memory with a lifetime of B. The program is rejected because B is shorter than A. The subject of the reference doesn't live as long as the reference. Listing 10-19 fixes the code so it doesn't have a dangling reference and compiles without any errors. Listing 10-19, a valid reference because the data has a longer lifetime than the reference. Here X has the lifetime B, which in this case is larger than A. This means R can reference X because Rust knows that the reference in R will always be valid while X is valid. Now that you know where the lifetimes of references are and how Rust analyzes lifetimes to ensure references will always be valid, let's explore generic lifetimes of parameters and return values in the context of functions. Generic lifetimes in functions. Let's write a function that returns a longer of 2 slices. This function will take 2 string slices and return a string slice. After we've implemented the longest function, the code in listing 10-20 should print the longest string is A, B, C, D. Listing 10-20, a main function that calls the longest function to find the longer of 2 strings. Note that we want the function to take string slices, which are references, because we don't want the longest function to take ownership of its parameters. We want to allow the function to accept slices of a string, the type stored in the variable string1, as well as string literals, which is the variable string2 contains. Refer to Stringing Slices as Parameters section in Chapter 4 for more discussion about why parameters we use in listing 10-20 are the ones we want. If we try to implement the longest function as shown in listing 10-21, it won't compile. Listing 10-20, an implementation of the longest function that returns the longer of 2 string slices but does not yet compile. Instead, we get the following error that talks about lifetimes. The help text reveals that the return type needs a generic lifetime parameter on it because Rust cannot tell whether the reference is being returned to refers to X or Y. Actually, we don't know either because the if block in the body of the function returns a reference to X and the else block returns a reference to Y. When we're defining this function, we don't know the concrete values that will be passed into this function, so we don't know whether the if case or the else case will execute. We also don't know the concrete lifetimes of the references that will be passed in, so we can't look into the scopes as we did in listing 10-18 and 10-19 to determine whether the reference we return will always be valid. The borrow checker can't determine this either because it doesn't know how the lifetimes of X and Y relate to the lifetimes in the return value. To fix this error, we add generic lifetime parameters that define the relationship between the references so the borrow checker can perform its analysis. Lifetime annotation syntax. Lifetime annotations don't change how long any of the references live, just as functions can accept any type when the signature specifies a generic type parameter. Functions can accept references with any lifetime by specifying a generic lifetime parameter. Lifetime annotations describe the relationships of lifetimes of multiple references to each other without affecting their lifetimes. Lifetime annotations have a slightly unusual syntax. The names of lifetime parameters must start with an apostrophe and are usually all lowercase and very short, like generic types. Most people use the name A. We place lifetime parameter annotations after the AND of a reference using a space to separate the annotation from the reference's type. Here are some examples: a reference to an I-32 without a lifetime perimeter, a reference to an I-32 that has a lifetime perimeter named A, and a mutable reference to an I-32 that also has a lifetime A. One lifetime annotation by itself doesn't have much meaning. Because the annotations are meant to tell Rust how generic lifetime perimeters of multiple references relate to each other. For example, let's say we have a function with the perimeter first. That is reference to an I-32 with lifetime A. The function also has perimeter named second that is another reference to an I-32 that also has a lifetime A. The lifetime annotations indicate that the references first and second must both live as long as that generic lifetime. Lifetime annotations in function signatures. Now let's examine the lifetime annotations in the context of the longest function. As with generic type perimeters, we need to declare generic lifetime perimeters inside angle brackets between the function name and the perimeter list. The constraint we want to express in this signature is that all the reference to the perimeters in the return value must have the same lifetime. We'll name the lifetime A and then add it to each reference as shown in listing 10-22. Listing 10-22, the longest function definition specifying that all references in signature must have the same lifetime A. This code should compile and produce the result we want when we use it with the main function in listing 10-20. The function signature now tells Rust that for some lifetime A, the function takes two perimeters, both of which are string slices that live at least as long as lifetime A. The function signature also tells Rust that the string slice returned from the function will live at least as long as lifetimes A. In practice, this means that the lifetime of the reference returned by the longest function is the same as the smaller of the lifetimes of the references passed in. These constraints are what we want Rust to enforce. Remember, when we specified the lifetime perimeters in this function signature, we're not changing the lifetimes of any values passed in or returned. Rather, we're specifying that the borrow checker should reject any values that don't adhere to these constraints. Note that the longest function doesn't need to know exactly how long x and y will live, only that some scope can be substituted for A that will specify this signature. When annotating lifetimes in functions, the annotations go in the function signature, not the function body. Rust can analyze the code within the function without any help. However, a function has references to or from code outside that function, it will become almost impossible for Rust to figure out the lifetimes of the perimeters or return values on its own. The lifetimes might be different each time the function is called. This is why we need to annotate the lifetimes manually. When we pass concrete references to the longest, the concrete lifetimes that is substituted for A is the part of the scope of X that overlaps with the scope of Y. In other words, generic lifetimes A will get the concrete lifetimes that is equal to the smaller the lifetimes X and Y. Because we've annotated the return reference with some lifetime perimeter A, the returned reference will also be valid for the length of the smaller lifetimes X and Y. Let's look at how the lifetime annotations restrict the longest function by passing in references that have different concrete lifetimes. Listing 10-23 is a straightforward example. Listing 10-23 using the longest function with reference to string values that have different concrete lifetimes. In this example, string 1 is valid until the end of the outer scope. String 2 is valid until the end of the inner scope, and the result references something that is valid until the end of the inner scope. Run this code and you'll see that the borrow checker approves this code and will compile it and print the longest string is long, string is long. Next, let's try an example that shows that lifetime of the reference and result must be smaller lifetime of the two arguments. We'll move the declaration of the result variable outside of the inner scope, but leave the assignment of the value to the result variable inside the scope with string 2. Then we'll move the print line that uses result outside the inner scope after the inner scope has ended. The code in listing 1024 will not compile. Listing 10-24 attempting to use the result after string 2 has gone out of scope. When we try to compile this code, we'll get an error. The error shows that for result to be valid for the print line statement, string 2 would need to be valid until the end of the outer scope. Rust knows this because we annotated the lifetimes of the function parameters and returned values using the same lifetime parameter a. As humans, we can look at this code and see that string 1 is no longer than string 2, and therefore result will contain a reference to string 1. Because string 1 has not gone out of scope yet, a reference to string 1 will still be valid for the print line statement. However, the compiler can't see that the reference is valid in this case. We've told Rust that the lifetime of the reference returned by the longest function is the same as the smaller of the lifetimes that references pass in. Therefore, the borrow checker disallows the code in listing 10-24 as possibly having an invalid reference. Try designing more experiments that vary the values and lifetimes of the references passed into the longest function and how the return reference is used. Make hypotheses about whether or not your experiments will pass the borrow checker before you compile, and then check to see if you're right. Thinking in terms of lifetimes. The way in which you need to specify lifetime parameters depend upon what your function is doing. For example, if we change the implementation of the longest function to always return the first parameter rather than the longest string slice, we wouldn't need to specify a lifetime on the y parameter of the following code. The following code will compile. In this example, we've specified a lifetime parameter a for the parameter x and the return type, but not for the parameter y, because the lifetime of y does not have any relationship with the lifetime of x or the return value. The returning a reference from a function, the lifetime parameter for the return type needs to match the lifetime parameter for one of the parameters. If the reference returned does not refer to one of the parameters, it must refer to a value created within the function, with which would be a dangling reference because the value will go out of scope and at the end of the function. Consider this attempt implementation of the longest function that won't compile. Here, even though we've specified a lifetime parameter a for the return type, this implementation will fail to compile because the return value lifetime is not related to the lifetime of the parameters at all. Here is the error message we'll get. The problem is that result goes out of scope and gets cleaned up at the end of the longest function. We're also trying to return a reference to result from the function. There is no way we can specify lifetime parameters that would change the dangling reference, and Rust won't let us create a dangling reference. In this case, the best fix would be return an own data type rather than a reference, so the calling function is then responsible for cleaning up the value. Ultimately, lifetime syntax is about connecting with lifetimes of various parameters and return values of functions. Once they're connected, Rust has enough information to allow memory-safe operations and disallow operations that would create dangling pointers or otherwise violate memory safety. Lifetime annotations in struct definitions. So far, we've only defined structs to hold own types. It's possible for structs to hold references, but in that case we would need to add a lifetime annotation on every reference in the struct's definition. Listing 10-25 has a struct named important excerpt that holds a string slice. Listing 10-25, a struct that holds a reference, so that definition needs a lifetime annotation. This struct has one field, part, that holds a string slice, which is a reference. As the generic data types, we declare the name of the generic lifetime parameter inside angle brackets after the name of the struct so that we can use the lifetime parameter in the body of the struct's definition. This annotation means an instance of important excerpt can't live outside of the reference it holds in its part field. The main function here creates an instance of the important excerpt struct that holds a reference to the first sentence of the string owned by the variable novel. In the data in novel exists before the import excerpt insistence is created. In addition, novel doesn't go out of scope until after the important excerpt goes out of scope, so the reference in the important excerpt instance is valid. Lifetime Allisyn. You've learned that every reference has a lifetime and that you need to specify lifetime parameters for functions or structs that use references. However, in Chapter 4, we had a function listing 4-9, which showed again in listing 10-26 that compiled without lifetime annotations. Listing 10-26, a function we defined in listing 4-9 that compiled without lifetime annotations, even though the parameter and return types are references. The reason this function compiles without lifetime annotations is historical. In early versions pre 1.0 of Rust, this code wouldn't have compiled because of every reference needed to explicit lifetime at that time. The function signature would have been written like this. After writing a lot of Rust code, the Rust team found that Rust programmers were entering the same lifetime annotations over and over in particular situations. These situations were predictable and followed a few deterministic patterns. The developers programmed these patterns into the compiler's code so that the borrow checker could infer the lifetimes in these situations and wouldn't need explicit annotations. This piece of Rust history is relevant because it's possible that more deterministic patterns will emerge and be added to the compiler in the future. Even fewer lifetime annotations might be required. The patterns programmed into Rust analytics of references are called the lifetime Allisyn's rule. These aren't rules for programmers to follow. They're a set of particular cases that the compiler will consider. And if your code fits these cases, you don't need to write the lifetimes explicitly. The Allisyn rules don't provide full inference. If Rust deterministically applies the rules, but there is still ambiguity as to what lifetimes the references have, the compiler won't guess what the lifetimes of the remaining references should be. In this case, instead of guessing, the compiler will give you an error that you can resolve by adding the lifetimes annotations that specify how the references relate to each other. Lifetimes on functions or method parameters are called input lifetimes, and lifetimes on return values are called output lifetimes. The compiler uses three rules to figure out what lifetime references have when they aren't explicit annotations. The first rule applies to input lifetimes, and the second and the third apply to output lifetimes. If the compiler gets to the end of the three rules and there is still references for which it can't figure out lifetimes, the compiler will stop with an error. This rule applies to FN definitions as well as input blocks. The first rule is that each parameter that is a reference gets its own lifetime parameter. In other words, a function with a parameter gets one lifetime parameter. Function foo a x and a I32. A function with two parameters gets two separate lifetime parameters. Function foo a b x and a I32, y and b I32, and so on. The second rule is if there is exactly one input lifetime parameter, that lifetime is assigned to all output lifetime parameters. Function foo a x and a I32 and a I32. The third rule is if there are multiple input lifetime parameters, but one of them is and self or and mute self because this is a method. The lifetime of self is assigned to all output lifetime parameters. This third rule makes method much easier to read and write because fewer symbols are necessary. Let's pretend we're the compiler. We'll apply these rules to figure out what lifetimes of the reference and signatures of the first underscore word function in listing 10-26 are. The signature starts without any lifetimes associated with the reference. When the compiler applies the first rule, which specifies each parameter get its own lifetime, we'll call it A as usual. So now the signature is this. The second rule applies because there is exactly one input lifetime. The second rule specifies the lifetime of the input parameter gets assigned to the output lifetime. So the signature is now this. Now all the references in the function signature have lifetimes, and the compiler can continue analysis without needing the programmer to annotate the lifetimes in this function signature. Let's look at another example, this time using the longest function that had no lifetime parameters when we started working with it in listing 10-21. Let's apply the first rule to each parameter. The parameter gets its own lifetime. This time we have two parameters instead of one, so we have two lifetimes. You can see that the second rule doesn't apply because there is more than one input lifetime. The third rule doesn't apply either because the longest is the function rather than a method. So none of the parameters are self. After working through all three, we still haven't figured out what the return type lifetime is. This is why we get an error trying to compile the code in listing 10-21. The compiler worked through the lifetimes Allisyn rules, but still couldn't figure out all the lifetimes of the reference in the signature. Because the third rule really only applies in method signatures, we'll look at lifetimes in context next to see why the third rule means we don't have to annotate lifetimes in method signatures very often. lifetime annotations, and method definitions. When we implemented methods on a struct with lifetimes, we used the same syntax as the generic type parameter shown in listing 10-11. When we declare and use the lifetime parameters depends on whether they're related to the struct fields or the method parameters and return values. Lifetime names for struct fields always need to be declared after the impl keyword and then used after the struct's name, because those lifetimes are part of the struct's type. In method signatures inside the impl block, references might be tied to the lifetime of references in the struct's field, or they might be independent. In addition, the lifetime Allisyn rules often make it so that lifetime annotations aren't necessary in method signatures. Let's look at some examples using the struct name impl excerpt. Excerpt that we defined in listing 10-25. First, we'll use a method named level whose only parameter is a reference to self and whose return value is an I32, which is not a reference to anything. The lifetime parameter declaration after impl and its use after the type name are required, but we're not required to annotate the lifetime of the reference to self because of the first Allisyn rule. Here's an example where the third lifetime Allisyn rule applies. There are two input lifetimes, so Rust applies the first lifetime Allisyn rule and then gives both and self and announcement their own lifetimes. Then, because one of the parameters is and self, the return type gets the lifetime of and self, and all lifetimes have been accounted for. The static lifetime. One special lifetime we need to discuss is the static, which means that the reference can live for the entire duration of the program. All string literals have the static lifetime, which we can annotate as follows. The text of the string is stored directly on the program's binary, which is always available. Therefore, the lifetime of the string's literal is static. You might see suggestions to use the static lifetimes in error messages, but before specifying static as the lifetime for a reference, think about whether the reference you have actually lives the entire lifetime of your program or not. You might consider whether you want it to live that long, even if it could. Most of the time, the problem results from attempting to create a dangle reference or a mismatch of the available lifetimes. In such cases, the solution is fixing those problems, not specifying the static lifetime. Generic type parameters, trait bounds, and lifetimes together. Let's briefly look at the syntax of specifying generic type parameters, trait bounds, and lifetimes all in one function. This is the longest function from listing 10-22 that returns the longer of two string slices, but now it has an extra parameter called an of the generic type t, which can be filled in by any type that implements the display trait as specified by the where clause. This extra parameter will be printed before the function compares the lengths of the string slices, which is why the display trait bound is necessary. Because lifetimes are a type of generic, the declarations of the lifetime parameter A and the generic type parameter T go in the same list inside the angle brackets after function name. Summary. We covered a lot in this chapter. Now that you know about generic type parameters, traits and trait bounds, and generic lifetime parameters, you're ready to write code without repetition that works in many different situations. Generic type parameters let you apply the code to different types. Traits and trait bounds ensure that even though the types are generic, they'll have the behavior the code needs. You learned how to use lifetime annotations to ensure this flexible code won't have any dangling references. And all of this analysis happens at compile time, which doesn't affect runtime performance. Believe it or not, there is much more to learn on the topics we discussed in this chapter. Chapter 17 discusses trait objects, which are another way to use traits. Chapter 19 covers more complex scenarios involving lifetime annotations as well as some advanced type system features. But next you'll learn how to write tests in Rust so that you can make sure your code is working the way it should. Okay, well, that concludes chapter 10. I believe we're halfway through this book. So if you've made it this far, halfway. I congratulate you, and hopefully you keep it up. If you need to, just play it again and again until you have it figured out. That's my plan. And on to the next chapter.